Hi, everyone, and welcome to the Chapter 9 lecture on the Introduction to the T-Statistic. We also call this the single sample T. At this point, we've looked at hypothesis testing with z-scores to see if an outcome is greater than what would be expected due to chance. However, the z-score formula requires more information than what we usually have. We don't usually know the mean for the population or the population's standard deviation. But that's kind of the whole point of research. We want to learn about and make inferences for a population. So what do we do? One option would be to run a single sample t-test, which allows us to test hypotheses about a population mean when the population standard deviation is unknown. But before we can run a t-test, we have to make sure we have all the needed pieces of information. When the population variance or standard deviation is unknown, we use a sample variance and sample standard deviation. We've talked about both of these in Chapter 4, where the variance is the sum of squares divided by n minus 1, and the sample standard deviation is just the square root of that. And remember that n minus 1 is there to account for unknown variance in the population. It's essentially providing us some wiggle room because there's some error when we take only a few people out of the population and then try to make inferences about them. But how would we handle standard error when we don't have the standard error of the population? For this, we would calculate estimated standard error, which is an estimate of the standard error when the population standard error is unknown. The calculation is similar to that of the population, which we discussed in Chapter 7. But the difference is that it uses the sample statistics from the previous slide. The estimated standard error is the sample standard deviation divided by the square root of the sample size. Alternatively, you could square the sample standard deviation, which is the variance, and divide by the sample size and square root the entire equation. If you remember from Chapter 7, when we do this, it can simplify the process when you plug it into a scientific calculator. And also, just know that as we move on to other tests in this course, we'll need to use the variance, so it would be helpful to get into the habit of using it now, but either equation is fine for this class. At this point, we can calculate the t-statistic, which is the sample mean minus mu, the population mean, divided by the estimated standard error. With the t-statistic, we also need to consider degrees of freedom, which we've talked a little bit about before. The degrees of freedom for t is n minus 1. So if you have 20 participants, the degrees of freedom is 19. By subtracting 1, we are correcting for using a sample. Again, we're just providing some wiggle room because there's likely some error between the sample and the population. Keep these calculations in mind, we'll come back to them. Before we jump into an example, we need to talk about whether a test is one-tailed or two-tailed, and whether or not an outcome is statistically significant. If you remember, a two-tailed test means that the outcome can fall into either tail of a distribution. We denote this with mu equals the population mean, or mu does not equal the population mean. So maybe we're interested in a new therapy technique meant to change the quality of life in adults with depression. Our null hypothesis would be that the new therapy technique does not affect quality of life in adults with depression. In other words, the mean of the therapy group is equal to that of the population. There is no effect of the therapy. Our alternative hypothesis is that the new therapy technique does affect the quality of life in adults. The mean of our group is different than that of the population. And note that the language here is a little vague. We're not hypothesizing that the therapy makes quality of life better or worse, just that it significantly changes it. When we have a one-tailed test, we have a specific hypothesis in mind. If we are hypothesizing that our group has a greater mean than that of the population, we would hypothesize that the mean would fall to the right of the distribution. Therefore, mu would be greater than the population mean, and therefore the null hypothesis is that the mean is less than or equal to the mean of the population. If we're hypothesizing that a sample has a mean less than the population, we would be hypothesizing that the scores would fall into the left tail, and therefore the signs would be switched. Mu would be less than the population mean, and the null would be that the sample mean is greater than or equal to the population. Since we typically expect therapy to help people, let's stay in the right tail. This means our null hypothesis is that a new therapy technique does not increase quality of life in adults with depression. Therefore, our mean is less than or equal to that of the population. Our alternative hypothesis would be that the new therapy technique increases quality of life in adults with depression. The mean of our sample is greater than that of the population. Again, the one-tailed test is different because there's a specific prediction here. A t-table is posted to Canvas so you can determine whether or not a t-statistic is statistically significant. This table works just like the others in this class, so I'll just go over it briefly. To find your critical value, you first need to determine your degrees of freedom. Again, this is n minus 1. From here, decide if the test is one-tailed or two-tailed. There are different rows for each of these. From here, you find your p-value, and in this class, we are just using the 0.05 p-value because that's the standard in psychology. If the t-statistic is greater than the critical value, it is statistically significant. Now we're ready for some examples. Say you hypothesize that the students in your dorm study more than the average student here at ISU. There are 16 people in your dorm, the average study time is 3.2 hours per day, and the variance is 0.64. We know that the ISU population studies for an average of 2.5 hours per day, but the variance is unknown. From here, we have 4 steps. First, we need to state the hypotheses. Then we need to set the criteria for a decision. Then we'll collect and compute the stats. And then finally, we'll make a decision on whether or not we can fail to reject the null hypothesis. Step 1, let's state the hypotheses. Remember that we are hypothesizing that the students in the dorm study more than the average ISU student. Therefore, this is a one-tailed test, and our alternative hypothesis is that the mean for the dorm is greater than the mean of the general population. Our null hypothesis is that the students in the dorm study less than or equal to the general population. From here, we need to set the criteria for a decision. Our p-value, which is listed here as alpha, is 0.05. There are 16 people in the dorm, so the degrees of freedom is 15. And for a one-tailed test, the critical value taken from the table is 1.753. From here, we need to collect and compute the stats. It looks like we're missing the estimated standard error, so we need to calculate that before we can calculate t. Using the estimated standard error equation, we have the square root of 0.64 divided by 16, which is 0.2. From here, we have all the information needed for the t-test. So taking that equation, we have 3.2 minus 2.5 divided by 2, which is 3.5. So our last step is to make a decision. 3.5 is greater than 1.753. So we reject the null. The students in the dorm study significantly more than the general students at ISU. Here's a practice problem for you to try on your own. The question is, do students in your 8 a.m. class differ from the average students on how much they consider themselves to be a morning person? The average student reports being a 4 on a scale of 1 to 10, and your class, on average, reported being a 3.46, with a variance of 3.10. There are 105 students in your class. Pause to solve. The answer will be shown in 5 seconds. In step 1, we state the hypothesis. Since there is not a specific prediction, this is a two-tailed test. So our alternative hypothesis is that the mean of the class does not equal the mean of the general population. Our null is that the mean of the class equals the mean of the general population. We set our criteria to p equals 0.05, our degrees of freedom to 104, and our critical t to 2. If the degrees of freedom is not listed, you go to the next lowest score. In step 3, we collect and compute our stats. Our estimated standard error is 0.173, and our t is negative 3.121. We always take the absolute value of the number, so when we go to make our decision, 3.121 is greater than 2.0. So we reject the null. The students in the 8 a.m. class significantly differ on how much they consider themselves a morning person compared to the general population of students. With different tests, we have different assumptions that must be met, or the statistics don't really represent our information. There are two basic assumptions for the t-test. Assumption 1 states that the values in the sample must consist of independent observations. In other words, each score is obtained without the influence from other scores. There's not other things affecting the data, and we'll talk more about this in future lectures. Assumption 2 states that the population sampled must be normally distributed. If the sample isn't normal, it can affect the statistics, especially if the sample size is small. So it's always better to have a larger sample size. Lastly, we can get an effect size for t, so we know how meaningful the result is. The larger the effect size, the better. Like with z-scores, Cohen's d can be used, but we have to estimate it because we don't have the standard deviation for the population. Instead, we substitute it with the sample standard deviation. For the equation, we have the sample mean minus the population mean divided by the sample standard deviation. The score you get from this is interpreted in terms of standard deviations. So if we have an estimated Cohen's d of 1.0, it would mean that the treatment effect is equal to 1 standard deviation. And you always look at the absolute value of the number. It doesn't matter if it went up or down, you were just looking at the difference. With this, let's find the effect size for the two previous examples. You can pause to solve if you would like, but I'll go ahead and solve this so you don't have to dig for your previous notes. For the study example, we have 3.2 minus 2.5 divided by the square root of 0.64. Because remember, we only have the variance, not the standard deviation. This gives us 0.875. So the mean difference is about 0.875 standard deviations. For the morning example, we have 3.46 minus 4 divided by the square root of 3.10, which is negative 0.307. The mean difference is about 0.307 standard deviations. Using this table, the effect size for the study example is large, but the effect size for the morning example is small. You can use this table for your homework assignments. And that is all I have for you. If you have any questions, please let me know.